Hi, in this video we will describe the Proximal Policy Optimization algorithm, or PPO, which is a reinforcement learning algorithm. The algorithm has, for example, been heavily used to post-train language models. We will first understand the algorithm and then we will implement it to train a model on the lunar lander task, which you can currently see in the background. In Lunar Lander, the goal is for the AI to safely land a rocket on the moon. As an input, some model gets 8 pieces of information related to velocity, position, angle, and the leg contact status. Then the model, at a given state, will output one of 4 actions. Do nothing, fire the left engine, fire the right engine, fire the main engine. More specifically, it will output a probability for each of those actions, which we will use to decide on actions later on. The model will continually receive rewards on its performance, and the goal is to make the model output probabilities for actions that maximizes the total amount of reward. That is, we want to increase the probabilities of the actions that yield high rewards and lower the probabilities of the actions that yield lower rewards. To do this, we normally calculate how much better an action is compared to the average. That is called the advantage, and we will showcase how to calculate it later. We multiply the advantage by the original probability and optimize this with gradient ascent to maximize the amount of reward the model receives, meaning that if the model predicts a high probability for an action that is better than the average, the multiplication becomes large and the model is optimized to increase that probability in the future. If the model predicts a high probability for an action that is worse than average, the multiplication becomes negative and the model is optimized to decrease that probability in the future. This simple algorithm is called reinforce, and it will be our foundation. However, there are some problems with this, and PPO builds on top of reinforce to solve them, which we will showcase now. One problem is unstable training. There is something called trust region optimization that tries to mitigate this by taking smaller optimization steps at a time. The idea is to continually keep an older version of the model and then ensure that the new version of the model, which we are optimizing, does not deviate too much from the old model. It stays in the trust region. PPO achieves this through clipping the change in output probabilities, that is the ratio of the new and old model between some minimum and maximum value. We can also see that PPO takes the ratio of the new model and the old model and multiplies that by the advantage. It is worth noting that we do this because we will calculate the advantages from the old model, and this ratio tells us how well the new model does on the old model's data. This is also called importance sampling. Therefore, we get how much more or less likely the new model is to take a certain action times how much better that action is compared to the average action of the old model. Furthermore, in RL, there is the problem of exploration versus exploitation. And in order to encourage the model to explore more, PPO adds a bonus if the output probability distribution is more uniform as compared to more certain, and this is called an entropy bonus. Now, one might wonder how to calculate these advantages. That is, how to calculate how much better an action is compared to the average. One way to do this is to have a so-called value network that tries to predict the average reward in a state from the state and onwards, which is then called the value. Then one can imagine that in the simplest case, the advantage is the reward at a current state plus all future rewards, which one may discount even, minus then the value at a given state. Notice that this is the reward at the current state plus the value at the next state minus the value at this state. Then, to train this network, one could make it optimize the square distance between the actual rewards and its predicted value. This is called the value loss. However, there is a more sophisticated technique to calculate the advantages called generalized advantage estimation. This idea combines both of our previous ideas, that is, discounting all future rewards and subtracting the value, which can be noisy if future rewards fluctuate a lot, and the method where you take a reward plus the value at the next state minus the current value, and this can be short-term biased, which is a problem. This new technique takes the difference between values at each time steps and combines them with a weighting that trades off this variance and short-term bias problems. Now let's implement a simple version of this. First, initialize the lunar landing environment from the OpenAI gym and implement some model with 8 inputs and 4 outputs for the lunar landing task. You create a copy of the new model and the old model and the value model, and then you train the new model on the lunar lander task using PPO. But first, using the old model, you go through some gameplays called a trajectory, collecting state, actions at those states, rewards received, and values in a given state from the value model. And then using these rewards and values, one can create the advantages using generalized advantage estimation. If one generated multi-trajectories in the initial phase, then one can normalize all these advantages as in a batch. Then one can train multiple optimization steps on those trajectories for both the new model and the value model with the PPO loss. Each optimization step for the new model looks roughly like the code here. It is worth noting that we are using gradient descent instead of ascent, so we have to add a negative sign in front. This is the main idea of the algorithm. Note that this is not the full code, but let's now train it on the lunar lander task and see how it performs.